Hi, and thank you for joining this class. In the next half an hour, we will take a closer look at the new and rapidly developing area of science, astrobiology, as well as the most exciting discoveries in the field. We will get to know what is necessary for life to emerge and develop, and how long will our Earth be able to sustain life. We will also take a journey to other planets in or outside our solar system and find out what are the newest technologies and recent missions in search of exoplanets and even life beyond Earth. Astrobiology addresses three fundamental questions that have challenged human imagination for centuries. What is the origin, evolution, and distribution of life in the universe, including Earth? So, what is life? Life is a surprisingly complex system, and it is very difficult to draw a line between life and non-life. According to the most widely accepted definition, life is a self-replicating encapsulated chemical system that undergoes Darwinian evolution. In other words, groups of related organisms have evolved in response to changes in the environment through natural selection. This process has been in effect ever since life began from simple organic molecules in water over 4 billion years ago. Life as we know it would be impossible on Earth without our atmosphere. The atmosphere is a layer of gas that surrounds the world, and in most cases it is surprisingly thin. On Earth, for example, about 2/3 of the air in the atmosphere lies within 10 kilometers of the surface. Why is the atmosphere so important? This thin layer of gas supplies the oxygen we breathe and the carbon dioxide which plants utilize. It also generates rain-giving clouds, and it protects all living organisms from the harmful cosmic rays and the ultraviolet radiation from the sun. One of the most important benefits the atmosphere provides is maintaining the Earth's temperature. On the Moon, which has no protective atmosphere, temperatures can range from 121 degrees Celsius in the sun to negative 157 degrees Celsius in the shade. Atmosphere also provides physical protection. More than 100 tons of space debris strikes Earth every single day, most in the form of dust and tiny particles. When they encounter the molecules that make up the Earth's atmosphere, however, the resulting friction destroys them long before they reach the ground. Even larger meteors can break up due to the stresses of atmospheric re-entry, and this makes catastrophic meteor strikes a rare occurrence. What is the atmosphere composition? The elements and compounds that make up the atmosphere and oceans evaporate readily under normal surface conditions. That's the definition of volatile. Life as we know it can occur only where a volatile such as water is stable in the liquid state, and where energy resources like sunlight or chemical energy are available for exploitation for making or supplying food. Such special conditions for life seem to be satisfied only on planetary surfaces. On Earth, volatiles that constitute the atmosphere are principally represented by the gases nitrogen, which makes up 78%, oxygen 20%, water vapor, the percentage varies according to weather and geography, argon gas about 1%, and carbon dioxide about 0.03%. There are trace amounts of other gases also. The Earth's atmosphere has changed over billions of years. From the beginning, a number of factors have affected the makeup of the atmosphere to change it from its initial state to what we have today. Several of these factors, such as plate tectonics, weathering of rocks, which tend to give them a reddish color as in the Grand Canyon, and chemical changes induced by the byproducts of life itself, are internal to the planet. However, external factors such as the slowly increasing luminosity of the Sun over billions of years, gradual changes in the Earth's orbit over many tens of thousands of years, and the rare but catastrophic impact of giant meteorites and comets have also played an important role. Some scientists describe three stages in the evolution of Earth's atmosphere as it is today. Earth's original atmosphere first appeared about 4.5 billion years ago, soon after the Earth and Moon completed their formational phase. It was probably just hydrogen and helium because these were the main gases in the dusty gas disk around the Sun from which the planets formed. The Earth and its atmosphere were very hot. Molecules of hydrogen and helium move really fast, especially when warm. Actually, they move so fast that they eventually all escaped Earth's gravity and drifted off into space. While the Earth's crust was still forming, the volcanoes were much more abundant than nowadays. The volcanoes released steam, carbon dioxide, and ammonia. Those greenhouse gases would have formed a thermal blanket over the surface of the early Earth. They strongly absorbed outgoing thermal radiation. This leads to a significantly enhanced warming greenhouse effect. A primitive crust solidified and cooled to the point where liquid water could condense. Water began pooling into the first lakes, seas, and oceans. Much of the carbon dioxide dissolved into the oceans. Meanwhile, the ammonia molecules in the atmosphere were broken apart by sunlight, leaving nitrogen and hydrogen. The hydrogen, being the lightest element, rose to the top of the atmosphere, and much of it eventually drifted off into space. The interaction of water, heat, and rock set the stage for the origin of life. The conditions on the surface were harsh because of the meteorite impacts and the daily ultraviolet radiation before the establishment of an ozone screen. So the first life probably have originated and subsequently evolved at the bottom of the sea. In the darkness of the ocean depths, it would have had to rely on chemical rather than light energy. An environment where this is possible, the deep-sea hydrothermal vent environments, has existed throughout much of the Earth's history along the mid-ocean ridges. Eventually, a simple form of bacteria developed that could live on energy from the sun and carbon dioxide in the water, producing oxygen as a waste product in the process known as photosynthesis. Only a tiny proportion of the oxygen in the atmosphere is made when ultraviolet light splits water molecules high in the atmosphere in a process known as photolysis. The main source of free oxygen is photosynthesis, which is also the dominant metabolic process that sustains the biosphere today. In order to convert light energy into chemical energy, photosynthetic organisms use molecular pigments like chlorophyll. With the development of photosynthetic bacteria, oxygen levels began to build up in the atmosphere, while the carbon dioxide levels continued to drop. Geological data indicates that starting about 2.5 billion years ago, sedimentary rocks began to become increasingly affected by higher amounts of oxygen in the atmosphere and appear red as though rusted. Scientists believe that at that time oxygen concentration began to rapidly increase because more oxygen was produced by photosynthesis than could be whisked away by reactions with the atmosphere, oceans, and rocks. A threshold had been reached which caused a crisis for primitive and anaerobic bacterial life, which is actually poisoned by excess oxygen in the environment. Such life still exists today in organic rich soils, swamps, deep in sediments, and lake bottom muds where levels of oxygen are low. This early oxygen crisis, however, created an opportunity and led to important new evolutionary changes as life responded to this challenge with metabolic innovations that made use of the newly available oxygen. Organisms evolved which used oxygen in their metabolic cycles to get 20 times more energy out of their food. These included organisms with a true cell nucleus, eukaryotes, from which all plants, animals, and fungi are descended. The final significant section in the emergence of an oxygen-rich atmosphere on Earth began about 700 million years ago when the fossil record documents the emergence of multicellular organisms. This free oxygen produced by photosynthesis is not only necessary for animals to breathe, but also for the formation of protective ozone layer in the upper atmosphere. When the oxygen levels became high enough, a little more than 1% of the present level, a powerful ozone screen started to form in the upper atmosphere that protects the first land-dwelling creatures from the sun's harmful ultraviolet radiation. Ozone is formed by the recombination of oxygen by solar radiation in the upper atmosphere into the new molecule with 3 oxygen atoms. Without an effective ozone layer in the upper atmosphere, more advanced life would not have been able to emerge from the seas to colonize the land. The vast bulk of oxygen is continuously replenished via plant photosynthesis. The high concentration of oxygen needed to keep the contemporary biosphere going is maintained despite its continual removal throughout oxidative processes like rusting, weathering, burning, and so on. If all photosynthesis were to cease, the oxygen in the atmosphere of the Earth would be mostly gone in less than a million years, along with the protective ozone layer. In his book Gaia, A New Look, A Life on Earth, James Lawlok emphasized that the atmospheric composition of the Earth is far from achieving chemical equilibrium with the surface and must be sustained by biological processes. According to this Lawlok-Gaia hypothesis, life is responsible for making the unique conditions for habitability on Earth. A coupled biological and geological mechanism, termed the carbon cycle, began to manifest itself early in the history of life on Earth, as life took over the production of organic matter and oxygen and began to regulate the balance of carbon between the atmosphere and the oceans. This cycle has helped to regulate the planet's surface temperature by balancing carbon dioxide output from volcanoes, burning and decay of organic matter, with weathering, burial of organic matter in sediments, and other means of removing carbon dioxide from the atmosphere. Over the past few hundred million years, the amount of carbon dioxide in the atmosphere has decreased from high levels to stabilize near its present relatively low level. Human activity, the long-term actions of plate tectonics and variations in Earth's orbit will inevitably cause large fluctuations in the amount of carbon dioxide in the atmosphere again, and perhaps changes in oxygen concentrations as well. What about the future? We call it hot future. What can we say about the distant future for life on this planet? The Sun will continue to grow brighter over the 5 billion years or so. Its luminosity has been increasing on a near linear path for more than 4.5 billion years because hydrogen is continually converted into the heavier element helium by nuclear fusion. The conversion releases tremendous amounts of energy every second and is responsible for sunlight. As helium accumulates, the average density of the Sun increases over time. This in turn causes pressure and temperatures in the Sun interior to increase. These higher pressures and temperatures increase the rate of fusion, and the extra energy that is generated leads to increased luminosity. In the end, some 5 billion years from now, much of the Sun's fuel will be exhausted. The Sun will begin to grow as it approaches the red giant phase of its stellar life cycle. By then, the oceans on Earth will have long since boiled away. The last live primitive bacteria residing in the deep crust of rocks and sediments will have perished. As the surface temperature rises, all volatile gases stored in the Earth's crust will be released to form a thick, hot blanketing atmosphere. Finally, there will be twin Venuses from that time until the end of the solar system. Recently, humanity has started a search for other Earths. Our neighbor Mars has long been thought as a probable home of extraterrestrial life. Both orbital and surface studies on Mars gave strong evidence that Mars had wetter and warmer periods, probably with rainfall, before 3 billion years ago. We conclude that Mars must have once had much thicker atmosphere with a much stronger greenhouse effect. But Mars now is a desert world, with a thin atmosphere and atmospheric pressure less than 1% of that on Earth's surface. That leaves the surface exposed to radiation and prone to huge temperature swings from day to night. If Mars was ever blue or green, it is surely red now. What happened? In 2013, NASA launched a robotic probe called MAVEN for Mars' atmosphere and volatile evolution to help resolve the mystery. According to data from MAVEN, much and possibly most of the Martian atmosphere has been lost to space, violently scraped from the planet by the solar wind. The solar wind is a steady stream of charged particles, mostly protons and electrons, emitted by the Sun. Earth is also in its path, but it has a protective magnetic field which Mars lacks. That wind streaming through space at several hundred miles per second creates its own magnetic field, inciting atmospheric particles to accelerate to high speed and then start carrying around, slamming into things. That process, known as sputtering, blew most of Mars' atmosphere gases into space. This was the conclusion of the MAVEN team. Why doesn't Mars have a magnetic field to protect it from the solar wind? The problem is right in the core of the planet. Mars had a magnetic field when it was young, and its iron core was molten and convecting, which is what Earth's iron core does this today. But Mars is smaller than Earth, and sometime about 4.2 billion years ago, that molten Martian core froze up. In this scenario, turning off the magnetic field meant turning on the effects of the solar wind, and Mars began losing its atmosphere. So let's take a journey far beyond Mars in our solar system and search for exoplanets. Beyond the solar system, astronomers have discovered over 3,700 exoplanets, including candidates and comfort bodies. It's easier to detect large ones, so nearly all are bigger than Earth and some are rather exotic. Hot Jupiters are Jupiter-sized planets within 0.5 astronomical units, or halfway from Sun to Earth, of their parent stars. Some are orbiting in only a few days. Then there are planets that sound like Earth on steroids, the super-Earths. These are up to 10 times the mass of our planet. Although harder to find, it's clearly just a matter of time before many Earth-sized exoplanets become known. How many will be habitable or even inhabited? Of course, before identifying a habitable exoplanet, we have to find exoplanets, and astronomers have developed two classes of methods. The first, indirect detection, looks for stellar properties such as position or brightness, which are affected by the presence of unseen planets. The second is direct detection of a planet within an image or a spectrum of its light. The four main indirect detection methods are astrometry, radial velocities, transits, and gravitational microlensing. The key to astrometry, as well as the radial velocity method, is that a planet and star orbit a common center of mass. For example, if a planet and star had exactly the same mass, they would orbit a point halfway between them. In reality, a planet is smaller than a star, so the center of mass is closer to the star and perhaps inside it. But in all cases, the star will follow a little orbit around the center of mass and wobble even when its planet can be seen. Astrometry measures the motion of a star in the sky using telescopes. It's sensitive to big planets far away from their star, but you have to wait many years or decades to track the effects of such planets on their star. The second technique, the Doppler shift or radial velocity method, relies on the fact that when the light of a star is split into all its colors, the spectrum has dark bands like a barcode. The elements in a stellar atmosphere absorb photons coming from the star's interior, which cause the dark lines. If the star moves toward or away from the Earth, the lines shift to higher bluer or lower redder frequencies, respectively. Everyone has expected the Doppler effect in sound. When a wailing police car approaches the sound waves are bunched into a high-frequency squeal, but after the car passes by, they become a low-frequency drone. A similar frequency shift occurs with light. A rhythmic red shift and blue shift of lines in a stellar spectrum shows that the star is wobbling and has a planet around it. The size of the shift indicates the mass of a planet, while the pacing gives the time for the planet to complete an orbit. In 1995, the first planet around a Sun-like star was detected using Doppler shift. It was a planet of at least half a Jupiter mass orbiting a star in the constellation of Pegasus. It is really close to its star, only about 7 million kilometers, and it makes a full orbit only for 4 days. This planet is a prototype of exoplanets called hot Jupiters, which are easy to find using the Doppler technique. But now we know that hot Jupiters are actually only a tiny minority of exoplanets, around 0.5 to 1%. One limitation of the Doppler shift technique is how we view the planetary system. If the orbit is phase-on, described as an inclination of 0 degrees from a plane perpendicular to the line of sight, there is no to and fro Doppler shift. The more general the orbit, the greater the Doppler shift. It becomes maximal at an edge of inclination of 90 degrees. There is often no way of knowing the inclination, so measured Doppler shift might be smaller than the ideal edge-on case, allowing us only to infer a minimum planetary mass. The next transit method measures the decrease in starlight when a planet crosses the face of a star, which can happen if we are lucky enough to view an exoplanet system virtually edge-on. Such geometry is statistically rare, but there are so many stars that if you gaze widely and long enough, transits will be seen. From the deep in the starlight using photometry techniques, telescope camera, it's possible to determine a planet's diameter if the star's size can be estimated. In turn, the planet's orbital period and distance from its star can be calculated from the cycling of the dimming. The fourth indirect method is microlensing. When an object passes between a distant star and us, Einstein's theory of general relativity predicts that the bending of light by the object's gravitational field. The foreground object effectively acts as a lens, focusing the light and making the distant star appear gradually brighter. But if a planet orbits a lens star, the background star can brighten more than once. This sensitive technique can find Earth's mass planets at orbital distance of 0.5 to 4 astronomical units around the star. For astrobiology, the most important techniques are direct detections that capture light from a planet. Direct detection is challenging because a planet is a dim body close to a vastly brighter star. Nonetheless, telescopes in space, such as the Hubble Space Telescope, and extremely large telescopes on the ground have accomplished direct detection using a coronagraph, which is a mask to block the starlight. The term coronagraph comes from techniques that were originally used to block out sunlight to study the sun's corona, which is the wispy halo seen in a solar eclipse. The results of exoplanet surveys to date generally show that the number of exoplanets increases at lower masses, so rocky, Earth-sized planets should be common. Density estimates for some exoplanets also allow assessment of composition. Density has been inferred using mass from the Doppler method and size from the transit methods. With density measurements, there are increasing clues about which exoplanets are made of gas, rock, water, or some mixture. As water is a requirement for Earth-like life, we are searching for bodies with liquid water. In the 1950s, the American astronomer Harlow Shapley talked about a zone around stars where planets could have liquid water on their surface. If a planet is too far away from its host star, it ices over, and if it's too close, it's too hot for liquid water. Nowadays, the term habitable zone refers to the region around a star in which an Earth-like planet could maintain liquid water on its surface at some instant in time. We specify a particular time because stars age and brighten or dim, so the habitable zone moves. In contrast to the habitable zone, the continuously habitable zone is the region around a star in which a planet could remain habitable for some specific period. Usually this is the star's main sequence lifetime, which is the period when the star is converting hydrogen to helium in its core. The width of the habitable zone around different types of main sequence stars, including the Sun, has been estimated. The inner edge is set by the planet's set ability to runaway greenhouse effect, while the outer boundary is usually determined by the failure of greenhouse warming when carbon dioxide is cold enough to condense into clouds of dry ice or dense enough to scatter away sunlight. For the Sun, the habitable zone's inner edge is around 0.85 to 0.97 astronomical units, while the periphery is 1.4 to 1.7 astronomical units. Around other stars, the habitable zone is closer in or further out, depending on the spectral class, which means whether a star is cooler or hotter than the Sun. For example, a star from spectral class K, which is cooler, would have a tight habitable zone from about the orbit of Mercury to that of the Earth. An even cooler M-type red dwarf star would have the center of its habitable zone at only 0.1 astronomical unit or so, well within the orbit of Mercury. M-dwarfs are the most common types of stars, making up about 3/4 of the total. In recent years, assumptions defining the habitable zone have been questioned. Conventionally, the outer edge is determined by the carbon dioxide condensation, but some large rocky exoplanets might have thick hydrogen-rich atmospheres. We know from studying Titan and the giant planets that hydrogen and methane behave as greenhouse gases, and these condense at far colder temperatures than carbon dioxide. Also, on the inner edge, a water-poor planet with polar lakes, rather than oceans, might not succumb to runaway greenhouse because it wouldn't have enough water to generate an atmosphere completely opaque to infrared radiation. Thus, the habitable zone might be wider than we think. And is there a galactic habitable zone? Some astronomers also argue that there's an optimal region in the galaxy for habitable planetary systems called the galactic habitable zone. They note that the Sun is 2/3 of the way from the center of the Milky Way, whereas a planetary system near the densely populated center would be perturbed by catastrophic cosmic events like supernovae and X-ray bursts or by passing stars. At the other extreme, stars near the galaxy edge are very poor in elements other than hydrogen or helium, and this might curtail planet formation. So let's talk about biosignatures, or how we find inhabited planets. The central question is whether we can find life. Generally, to determine an exoplanet's properties and look for life, we need a planet's visible or infrared light spectrum. Different molecules and atoms absorb different frequencies in spectra. Thus we can look for atmospheric gases such as oxygen or methane that can be produced by life. Such planetary features that indicate life are called biosignatures. In 1990, the Galileo spacecraft, which was headed for Jupiter, obtained spectra of Earth. It was a sort of dry run for exoplanets and showed that you could detect Earth's atmospheric oxygen, methane, and abundant water. Abundant oxygen in the atmosphere of a distant world might indicate the presence of life, as we don't know any non-biological way to produce an oxygen abundance as high as on Earth. What is more, the simultaneous presence of oxygen and methane is evidence for life because these two gases should quickly react with each other unless a biosphere is producing great amounts of them, which prevents equilibrium. Thus we say that Earth's atmosphere is in chemical disequilibrium. That's the kind of biosignature we would like from exoplanets. Already, some information has been collected about exoplanet atmospheres by looking at differences in spectra when transiting exoplanets pass behind or in front of a star. The spectrum in the primary transit when a planet crosses the phase of a star includes light passing through a ring of atmosphere around the planet. So subtracting the spectrum of just the star after the planet has passed by can isolate the spectrum of the planet's atmosphere. Alternatively, you take a spectrum when the planet is behind the star in its secondary transit, and you subtract that from a spectrum of the planet plus the star when the planet is beside the star. This produces the spectrum of the whole planet. In fact, this technique has been used to obtain infrared spectra of hot Jupiters with the Spitzer Space Telescope. Some of the current and near-future approved missions and facilities are pushing the frontiers of the study of exoplanets and the search for potentially habitable worlds. The Hubble Space Telescope, launched in 1990, is a 2.4-meter telescope in low Earth orbit. It is one of NASA's 4 great observatories. The Space Telescope imaging spectrograph was used to obtain the spectrum of the atmosphere of several gas giant planets orbiting very close to their host stars. The spectrum was obtained using transit spectroscopy. Hubble Space Telescope is also able to obtain direct images of exoplanets, but only for very large planets, several times the size of Jupiter, that are orbiting very far away from their host stars. The NASA Spitzer Space Telescope is an infrared observatory in an Earth drift-away orbit. This means the Spitzer telescope is orbiting the Sun in the same path as Earth, but is getting slowly farther away from Earth each day. Spitzer was launched in 2003 and is able to conduct observations of exoplanets that eclipse or are eclipsed by their host stars. Using the subtle change in the brightness of the star as this occurs, astronomers estimate the size and the mean temperature of the exoplanet. Kepler telescope was launched by NASA to discover Earth-sized planets orbiting other stars. It operated from 2009 to 2013 from an orbit around the Sun, staring continuously at 145,000 main sequence stars in the constellation of Cygnus, the Swan, to look for transits where most of the stars are 500 to 3,000 light-years away. Kepler has found over 4,000 exoplanet candidates, which are confirmed by checking for periodic dimming or using another detection technique such as Doppler shift. Over 2,300 are confirmed and 30 are Earth-like planets in the habitable zone. Most of the exoplanets are too far away to study in detail, like getting the spectrum of atmospheres. However, Kepler was designed to accurately determine the size distribution of exoplanets. It has successfully achieved this goal. In May 2014, NASA announced the approval of extending the Kepler mission to K2 mission Second Light. K2 involves using Kepler's remaining capability to collect data for the study of supernova explosions, star formation, and solar system bodies such as asteroids and comets, and studying more exoplanets. In mission's plan, Kepler would search a much larger area in the plane of Earth's orbit around the Sun. In December 2014, the K2 mission had detected its first confirmed exoplanet. The mission is extended until the exhaustion of onboard fuel in 2018. NASA's Transiting Exoplanet Survey Satellite, or TESS, was launched using SpaceX Falcon 9 rocket in April 2018. Over the course of 2 years, TESS will search approximately 200,000 nearby stars for the presence of exoplanets using the transit technique. TESS is the first all-sky exoplanet mission, and the stars TESS will study are all within 200 light-years of the Sun. This means that many of the exoplanets that TESS will discover will be suitable for more detailed follow-up observations and for search for biosignatures with the James Webb Space Telescope, ground-based telescopes, and even more advanced telescopes of the future. The James Webb Space Telescope is an observatory with a segmented 6.5-meter primary mirror. It is scheduled for launch in 2020 and is optimized for acquiring data in the infrared region of the electromagnetic spectrum. James Webb Telescope will be capable of pursuing many astronomical research topics, and studying exoplanets is one of its prime areas of investigation. James Webb will use transit spectroscopy to study the properties of exoplanets orbiting nearby M dwarfs. James Webb will be able to get high-quality spectra of the atmospheres of a number of exoplanets around these cooler stars. In conclusion, we can say that astrobiology is a complex science field which utilizes the joint efforts of biologists, astronomers, chemists, and geologists to develop a better understanding of life and our place in the universe. Thanks for your attention.